Hello everyone, welcome to this video. My name is Emerson Ahrari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to do downscaling process for GRACE data, a popular dataset for the groundwater monitoring in the Google Earth Engine platform. Let's go to the tutorial. So, in the first step, we need to select our region of interest. For example, I'm gonna select a wide region or very big region as a region of interest because the GRACE data spatial resolution is around 50 km per pixel. That's why we need to select a wide region to have enough pixels for the downscaling process. And the initial resolution is 50 km in the GRACE data, and I want to improve it to 10 km. That could be very useful for the remote sensing and GRACE users. So stay with me in this tutorial and follow my YouTube channel and share it with your community. So in the first step, I'm gonna select my study area through the drawing tools available here. For example, here there is a rectangle tool helping me to draw a rectangle for the region of interest. For example, the European countries and also part of Asia and Russia is selected in the region of interest. I'm gonna do downscaling for this region. So after region of interest selected, you will have it as a geometry in the main panel. So in the next step, I need to call GRACE data in the Google Earth Engine platform. Make a new variable as GRACE equals to, go to search places and dataset and type GRACE. As you can see, various GRACE products available with monthly spatial resolution, with monthly temporal resolution. As you can see, the global mascon CRI filtered data is available here and imported into the code. So if you go to the data description, you will see a lot of information about the data characteristic. For example, the dataset is available since 2002 to now, and also if you go to the bands, you will see that the spatial resolution is 55 km. That is too big, and the target band is LWE thickness or equivalent liquid water thickness in centimeter. That is the target band that we need to improve its spatial resolution from 50 km to 10 km using different predictors in the Google Earth Engine platform. So back to the code and assigning image collection to the GRACE. Then define a period of time in which you want to do the downscaling process. So for example, in this tutorial, I'm going to select a 1 year, for example, 2020, in which I want to do downscaling for every month using different predictors. Two variables created to define the time. First is the time start, the time starting from 2020, and the time ends to 2021. But remember that 21 not considered in the temporal period, and the time period I have starting from the January and ends to December. That filter date will include time start and time end here. If I print GRACE data in the right panel, you will see that 12 elements for 1 year is available. For each month, one liquid water thickness is available. As you can see, two different bands, the LWE thickness and uncertainty band is available, but the target band is LWE. That's why using that select, I'm gonna select only the target band. That select is a function helping us to find the target band and separate it from others. Save your code and run it again. Again, you will have 12 elements, one image for each month, and it is including LWE thickness. So if you want to have a visual preview for the GRACE data with 55 kilometer spatial resolution, map.app layer is the best tool that helping us to do visualization for our product. So couple of arguments we have. Some of the users asking me about how to show the arguments like this. It's very simple. When you write the code inside the parentheses, if you press on Control and Space together, all of the arguments listed here. So instead of object, I want to see all GRACE data that is stacked into a single TIFF file through those two bands and then clipped based on the region of interest. Leave the visualization parameters empty and the layer name could be, for example, GRACE 55 kilometer and shown equal to false because I want to avoid automatic visualization because it highly reduces the speed of processing. Save your code and run it again. As you can see, after a few moments in the layers, there is a GRACE 55 kilometer available. You can turn geometry off and also to have a better visualization, go to the layer setting and pick the date or the time or the band that you want to do for the that you need for the visualization, and then apply a stretching method and click on apply again and check it on, and here is the data with 55 kilometer spatial resolution that is too coarse for the studies, and also you cannot detect most of actually changes inside of each pixel. That's why we need to do the downscaling for such kind of data to 10 kilometer. That highly improves our abilities to work with this data with more spatial detail. So now I want to show you what kind of predictors we need for the downscaling process, because as you know, in the downscaling using a statistical approach, we have one dependent variable and couple of independent variable or predictors. So here, for example, all the variables that directly or indirectly is related to the groundwater and also the water content should be considered in this study, such as the precipitation, such as, for example, precipitation, soil moisture, and snow-related parameters, snow weather equivalent, and snow cover, and on it goes. And also the land cover also should be considered for this study as a predictor. So now I'm gonna call all of the predictors separately one by one in different variables, and then we want to combine all the predictors and target variable into a single file. So let's get started. Most of the variables available in the FLDAS product. The FLDAS is one of the assimilated remote sensing data that is available in the Google Earth Engine platform, and most of the parameters we need available in the FLDAS. If you go to the data characteristic, you will see that this product is available since 1982, and in the bands the spatial resolution, that is very important, is around 11 kilometer. That is still good for our study because we want to improve our spatial resolution from 55 to 10 or 11. 1 kilometer is not very important here, so that could be a good target for our studies. So, and also most of the predictors we need available in this product, for example, all of the snow related parameters such as the snow cover, snow depth, snowfall rate, and also the precipitation, and also the soil moisture for the soil top layer. All of them is available here, and also snow weather equivalent here. These are very good predictors for the GRACE data. If you followed my previous tutorial about the downscaling for example, soil moisture and precipitation, definitely you know that for when we want a downscaling process in the Google Earth Engine or using a statistical approach, it is very important to select those of predictors that directly or indirectly is related to the target variable. The target variable is grace, is related to the water content and also the water storage. And now all the parameters that is related to the water and water storage in our study area, such as runoff and other water parameters, could be considered as a predictor in this tutorial. So now I'm starting with FLDAS because it is including couple of variables I need. FLDAS equals to, so here image collection number 2 is gonna assign to FLDAS image collection number 2, and then we need to filter FLDAS data based on time start and time end, because for the corresponding dates and months we need to have the target variable grace and also the predictors or FLDAS bands, time start and time end here. Then we need to select the predictors here. So go to the data characteristic, open it up into another page, and here as you can see here in the bands, here you can see the list of variables available here. For example, if I type snow by Control F, you can see that all the snow cover products, most of them starting with snow. For example, snow cover, snow depth, and snowfall. So here, back to the code now, and then through the dot select, I need to call all the bands starting with snow. And also the other bands could be selected by their name. For example, the next one is a snow water equivalent here. You can copy and paste it as the target, as a predictor. And the other parameters such as the soil moisture and snow cover, soil moisture, and also the precipitation, total precipitation rate should be considered here. Soil moisture and total precipitation. These are good predictors helping us to model a higher resolution grace data. Not 10, because the 10 kilometer relatively for the grace is a high resolution, but typically 10 kilometer is not very high, is not high resolution. It is a part of course resolution data, but when the initial resolution is 55 kilometer, in this situation the 10 kilometer could be a higher spatial resolution. That's why I'm saying that higher spatial resolution. So the FLDAS data is available. Now I'm printing this variable. As you can see, same as the grace or target variable, we have 12 elements here, one element for each month, and each image including snow cover, snow related, and also the water related parameters such as soil moisture and also the rainfall. That could be very useful for our modeling. So in the next step, I need to call land cover product that helping us to separate the different land covers. That could be useful things. One of the most useful predictors in all downscaling scenarios in my experience. So now make a land cover map through the modis data variable land cover equals to, go to search places and dataset and type land cover or modis land cover. The modis land cover with 500 meter spatial resolution globally is available with annual temporal resolution. Import it into the code, and then image collection number 3 here, image collection number 3 assigning to the land cover, and then through the select you can select the target land cover map, that is LC type 1. This is the band that typically used as the modis land cover map, LC type 1. Copy and paste it into the code. So now LC type 1 is selected, and now I want to make a unit integrated, a single land cover map for my study area using that mode. Mode, as you know, is a statistical parameter that's helping me to find the most frequent classes during the time over the last 20 years. This could be help us to detect, to make a better modeling for our study area. So the land cover is also ready, and now I need to make a single collection to combine or bringing the target variable and predictors into a single collection. This is a very important thing. So if you want to do this, first we need to make a single, actually make a same property according to the date information for the GRACE and FLDS data, and then we can combine them based on the same properties using the join function. For example, here through the map, I'm making a new function that each input image considered as IMG. Now I'm making a variable as date because I want to make a single property as a date that's showing the date information with the normal format, not with the millisecond format. Because already, as you can see, the date information here mentioned by millisecond format, but I want to show them by year, month, and day. Or year or month because the data is monthly, and then I will join them based on the correspond months. So the date from each input image, its date extracted, that date by date function, and format helping me to make a format for the extracted date from millisecond to the normal format, year, and also the month. And finally, each input image returning with the new properties. First, I need to have the existing properties or the previous properties, and then through that set, I can make a new property. The new property could be date equal to date. So now if I print the GRACE, you will see in the right side again same number of images we have, but one new property added. This is the date, and I want to do the join process based on this new property. Then we need to repeat this function same as we have for the GRACE, but this time I want to apply it on FLDS data. As you can see, this is the FLDS data. A new property as date is created for the FLDS based on months. Now print the FLDS. In the right panel, again 12 elements is available, and one of them is the date. This will be the target properties that we can do the join process based on. This is the land cover. So, and the next one is the land cover, but land cover is a single band that we can add it into the next step. So how we can bring them into a single collection? This is the question. If the initial and target variables, coming from the same sensor or same satellite, it's very easy, and we can use that combine, same as I showed in the previous tutorial. But here they are not from the same sensor. They are, the FLDS is an assimilated product. It's a combination of the models, in situ, and satellite data, and the GRACE coming from the GRACE satellites. That's totally different sources. So now I want to bring them into a single collection using join function. A new variable as join is created equals to EarthEngine.join.inner. So the inner join helping me to join these together. And then I need to make an equal filter because I want to find those of images that date information is same. For example, the date with this format, one of the same one will be in the grace, and I want to gather the same data into a single layer stack now. So I will show you in the next step. If it is a little complicated for you, but in the next step you will understand better. So EarthEngine.filter.equals. I want to make a filter to join the data based on date properties. Equal means the right field and the left field for two input collection should have same date information. So one argument is left field equals to date, and the next one is the right field equals to date. Means I want to join data that's date will be is same between them. So now join collection equals to, so EarthEngine.image collection, bringing a whole of process into image collection format. It is very important things, and then bring join here that apply on primary and secondary variables. The primary variables is FLDAS. The first collection is FLDAS. The second collection is grace data, and condition that we want to apply these the condition that we want to join these two based on is the filter. We want to join these two based on same date, as you can see already created. So that filter, and then make a print join collection to see the result. In the right side we have again 12 features. For each date, as you can see, we have a primary properties and secondary properties. The primary properties is FLDAS data for January of 2020, and secondary is LWE thickness grace data with the same date for January of 2020. So this is repeated for all other variables we can see here. It is very simple thing. So, but now these are properties. As you can see, these are not single or separate bands. These are a part of properties. Now I need to write a code to bring them out from the properties and convert them to a single bands or concrete bands for the further analysis. Make a new variable again, and now here, or even we can do it in the next part or in another variable. No matter, you can continue the process through the dot map, or you can continue it through another variable. So join collection, the final collection will be like that. Get join collection first, make a loop for each feature input, each input feature. Here we have no image. For each date we have a feature with two properties. As you can see, this is mentioned feature with two properties, primary and secondary, that we want to convert them to the image format. So now make a variable for primary EarthEngine.image. Whenever you want to bring something, or whenever you want to select something from the property, you need use get. As you can see, that's get primary, just like that. And then for secondary, EarthEngine.image from input image that get secondary. The secondary also selected here. So and also we have the land cover. That means when the code returning primary dot add bands with secondary, we need to add the land cover for each month. That's how it's working. Now I'm printing the collection. IMG is not defined. It is true because the input argument is feature. Run the code again. A new image collection created with 12 elements in which for each month we have Grace and FLDAS products, and also the land cover data should be available. That add is wrong. Should be that add bands. Run it again. And now you can see that for each month, land cover, FLDAS product, all of them with 10 km spatial resolution, and also the Grace data is available here. For all months, we have 8 elements. It is good. So now the collection is ready and we can go through the modeling process. Let me to make a bigger space for coding, helping you to see better. Yeah. And now we want to make a loop to do the downscaling based on random forest model for each month separately according to the relationship between between the target variable, that is Grace, and also the predictors such as land cover and FLDAS data. Make a new variable as a Grace 10 km with 10 km equals to get the final collection including target and predictors together and bring them into a loop using a function each month's image considered as an IMG here. And first we need to collect the training data automatically. So a new variable as training is created from each input image that a stratified sample, helping us to collect the samples automatically based on Grace data. So the first is the number of points. The number of points equal to how number of points or how many samples you want to collect for each single value in the Grace data. For example, I want to collect 100 samples per pixel or per a single value or unique value. And then the class band equals to, the class band is the target band, the band we want to improve its spatial resolution, that is LWE thickness. So, and the region of interest equals to the geometry, and a scale should be set according to the target spatial resolution, that is 10 km or 10,000. So now a stratified sample collects the training data with these characteristics. So in the next level, according to the training data, I need to make a model with random forest and train it based on these data. So a new variable as model equals to earthengine.classifier.random forest. A small random forest is one of the best classifier and regression methods in the machine learning that helping us to model between the target and predictors, specifically when the relationship is not completely linear. So for the more complex relationship, the methods such as a random forest works very well. So the small random forest here, and the number of trees experimentally I'm using 80, and most of the time works very well. But I have no reference for the tree numbers or something like that. But experimentally, whenever I use 80, I got a good result. So now I'm gonna train this model based on the training data. So a couple of arguments for train we have. For training we need, one of them is features equal to the training, and the class property, you can copy and paste it. The class property is the target band, LWS thickness, and the input properties is band names. The input properties is band names. From input image, select band names. Very simple. So this is a classifier model, but we need to convert it to a regression model. For some of the classifiers, such as minimum distance, random forest, and also smile cart, and some of the methods, we can use the regression format in the analysis because they are not only the classifier. For example, for support vector machine, at least in the Google Earth engine, you cannot use the regression style. Set output mode, regression, just like that. So now I want to apply do the modeling process or apply the model or run the model based on the predictors. First, I need to select the predictor band names. Band or bands equals to, from each input image, select the band names that remove all the predictors, only should be selected without LWE thickness, without grace data, because this is the target variable. All of the predictors should be selected because the input for model must be the predictors, not the target and predictors together. So now the result equals to, from each input image, I'm selecting the predictors using .select and then doing classification or regression analysis based on the model that I have created. The file name will be grace with 10 kilometer and dot to float, helping me to convert the data format to the float. But remember that the input, the target variable should have integer format. It is very important. That's why I'm using that to integer in the first lines. Actually, when the img returns for the grace, that to integer, helping us to convert its value to integer format, to unsigned integer, because it's including some of the positive and negative values. That to unsigned integer should be selected, or unsigned or to integer, no difference. If we had a problem, we can select one of the unsigned integer, 16 bits or 32 bits or 8 bits. So now just that to integer is enough, and back to the final part, and finally function returning the result with the properties of input images, just like that, as you can see here. And now I'm printing the grace 10 kilometer to see if it works or not, because if there is any problem during the model or modeling process, you will see after printing. So there is no error here. For each date, we have one grace data with a 10 kilometer spatial resolution. So now we need to do a visual comparison. Recently, or a few minutes ago, I have used map.addLayer for the 55 kilometer data. Now we can repeat it here, this time for 10 kilometer data. Now I want to visualize grace data with 10 kilometer that is stacked in each date that stacked all together for 1 year and clipped based on the region of interest, and the band name is Grace 10 km. Remember to save your code and then go to the map and run the code again. So now we have two Grace data. First, let's go through the visual assessment for the January image. The first image in the 55 kilometer data, the range of value starting from -12 to 14. Apply and check it on. This is the original image or the target variable we had, and now we want to see the predicted value. The predicted value here for the January, and increase its contrast, and also the value ranges from -18 to 15. It is normal if we have some changes in the minimum and maximum value. Click on apply and check it on for the Grace data. So this is the downscaled product for the January, and also this is the original one. The original one is like that, and downscaled one is like this. As you can see, it's worked very well, and also now you can see the details of the downscale, details of the actually Grace data with more spatial detail with high quality. Also, it's very useful product. And now you can check it on for different dates. For example, one of the dates, this is for August. For example, this image for August, and I'm showing it with 1 sigma stretching techniques for 55 kilometer data. This is the August image, and now I'm selecting the August image here and increasing in its contrast again. This is the final product we created. So I hope you liked this tutorial, and also that was the way of downscaling process for the data. And now in the next step, if you want to get export from the 10 kilometer data, it is very easy. Just use .export.image to drive, export.image to drive. Couple of variables we have here. The image we want to get export. The target image is Grace data with 10 kilometer stacked version and clipped based on the region of interest, that is geometry. And the description, the file name will be the Grace 10 kilometer, and also the region of interest is geometry. Scale or pixel size equals to 10,000. CRS coordinate system EPSG 4326. This is for WGS 84. And then if you want, you can define the destination folder. That could be test in my Google Drive, but you can choose any other name for the destination folder. It is optional and up to you. Finally, save your code and run it again. Run it again, and 12 elements is available. Go to the task here. It's ready to save. Click on run, and then click on run again. So it's under process, and after a few minutes the data will be saved and available in your Google Drive for download and checking in desktop software. So I hope you like this tutorial, and also I tried to show you how we can do downscaling for the Grace data as simplest as possible. If you had any question or problem regarding this code, first of all, compare your code with mine, because the code link is available below this video in the description box on my YouTube channel. And also, if you had any question, again, you can reach me out in the comments, and also I will be happy if I can help you to handle this code for your project. Thank you for your attention.